Okay, welcome class. I am going to explain thermodynamics. I am your teacher, Javier Diaz, and let's start with the introduction of very simple topics of thermodynamics. These basic topics, and I have made a summary for you, and I hope it is easy to understand, that you can skip or that you can not skip, that you can read the book with this, any book of thermodynamics, and I try to make it very simple for you. So I will skip this part because this is not important right now for the class. And yeah, this is what is important. So we're going to see some introduction about what is thermodynamics. And to be honest, thermodynamics is fascinating. It's one of those subjects that if you see it with care and you research a lot, you tend to be fascinated with it. And the thing with thermodynamics is that it is physics, but about energy, and everything functions with energy, even us. It is essential in life. So we can go from microscopic organisms to electronics using home, and obviously it is used at engineering. So that's why I am focusing on this part. As engineers, we tend to use thermodynamics as a way of doing things. For example, in motors, thermodynamics is very used in other things, but it is fascinating. Just bear with me these few minutes, and I hope you find it fascinating as me. So basically, thermodynamics is the science of energy. That is very simple, and we're going to see some basic concepts like energy, system, state, and process. So what is energy? Energy is a little bit difficult or weird to define. So let's just say that is the one responsible to generate changes. What type of changes? We're going to see those in a moment. So each slide contains information that will be useful during all the class. Every slide is related to the other ones, and I tend to work with keywords, and I like to use a lot of keywords, like energy, for example, is a keyword, and changes, generate changes, will be the other keywords that I want you to remember during the classes. And it will make you easy, it will make it easy, to just keep going. What I mean is that you will not have to find definitions in a book or to memorize them if you know the keywords. So it is one of my teaching methods or studying methods also. Use keywords and make questions during all these slides, but that will be topic for another video. So let's focus on energy. So one of the first principles used in thermodynamics is the principle of energy conservation. I am very sure that all of you know it, and it establishes that the energy may change the form, but it will remain the same in quantity even after changing. So the total energy remains constant. So if energy was in a state and then changing to this one, we can get it back to the first state or change it to another one, but we won't have the energy will not disappear. It will only transform. Maybe it will transform into heat or into calories or something else. For example, here's an example, very easy to see why is it important, and it's about eating. Someone who ingests more energy, calories, than the energy it uses when he's doing or she's doing exercise will be transformed into weight. So if I eat more than what I use at the exercise, I will gain weight. But if I do more exercise, the calories will become less. So the energy will be wasted or consumed by the exercise. So here's a little formula, and remember that the triangular shape is delta, and delta means changes. So going back again, changes, keywords, delta, changes. So the change in the energy that enters minus the change in the energy that go out will be equal to the changes in energy. So this is the principle of energy conservation, and you can state it into a formula too. And first law and second law of thermodynamics. The first law is this one. It is just an expression of the energy conservation principle, and it states that the energy is a thermodynamic property. We're going to see what is a property. And the second law of thermodynamics establishes that the energy has quality and quantity, and processes occurs towards to where the energy decreases. So I think this will explain the second law of thermodynamics. This is an example of some hot cup of coffee, and these coffee cups will transfer its energy to the system around it, to the table, to our bodies, to the air, and at a certain point the cup will get cold. Well, if it is hot, but if it is cold, the opposite will happen. The coffee will get warm, and it will absorb the heat from the environment, from our bodies, or from the table. So that is the second law of thermodynamics. It says that the energy will go towards where the energy has less potential, like where it has less energy. In this case, from warm to cold, and vice versa, from cold to warm. And we'll reach why does it do that later on, and that has a name. Just wait a little bit. So we have some examples here. We have a solar panel and a stove, and they are using energy from the sun to do things. So that's a good way to apply this, and they're environment friendly. So this is a good project. You can do it. It is not costly, I think. Well, I have made this one and it is not so costly, and I am sure that this is not expensive at all. And what is interesting about this slide is that you should try it, because by doing projects you will learn how to apply thermodynamics, and you will search for the calculations that you need in order to get it done. Or you can use try and error, but you will waste a lot of resources. But it can be done both ways. What do I recommend? Well, I recommend to research first and then apply it. And what is a system? I already talked about system, and it is an important concept to know. It is defined as the quantity of matter chosen to analysis. And the system is everything that is inside that we have chosen, and the outside will be those things that are not chosen that can affect the system. And we have border, where the things in our system will be kept inside. So also there are two types of systems, closed systems and open systems, and I don't think this needs a lot of explanation, but closed system is something like this. No matter what, nothing can get inside, but energy can cross the border and volume can change inside this closed system. However, open systems are like they have inputs something can enter the system, and basically we can control the quantity of the thing that we are getting into the system. In this case, we have water coming into the tank and water going out of the tank. So this is an open system because we can modify the inputs. And we also have something called properties, and it is a characteristic. Well, every characteristic is called a property. So one example of these are physical properties like volume, pressure, temperature, mass, weight, force, etc. Those are properties. And I think we mentioned that before. Let me go back a little bit here. So the first law of thermodynamics says that the energy is a thermodynamic property. So if we have physical properties, we have thermodynamic properties, and one of those is energy. So going back to properties, here we have two types of properties: intensive and extensive properties. So energy is a property of thermodynamics. It is a characteristic of thermodynamic systems. And intensive properties are the ones that are mass independent, like temperature, pressure, and density. And extensive properties are the ones that depend from the size of the system extension. So the bigger the system, the bigger the properties, or the more properties that we can have. So a state, what is a state in a system? We already know what is a system, where there is no change in its properties, in its characteristics, or that can be calculated. This allows to describe all the properties. So what do I want to say here is that if we can calculate the system, if we can calculate the properties, if we can say that there is no change in the system, we call that a state. So we are in a specific state where all values are known, where nothing is changing. So we have a state. What kind of a state? We can have an equilibrium state, and we can be in a thermic equilibrium state, or in a mechanic equilibrium state, or in a chemical equilibrium state. Equilibrium means that nothing is changing. It is in equilibrium. The stats are in balance. The stats are not changing, or there is no external forces or external properties outside of the system that are affecting our system. So these are states, like equilibrium states. And we have also the process and cycle. So if we are going to change the state of our system and we want to change a property, we have to go through a process, and we can repeat it and repeat it and repeat it as a cycle. And a quasi-static process is the process that is in an equilibrium state. Okay, so I think this is very simple. I think the images will help you remember about this, and I will skip the homework part, and we have some units. So in order to understand thermodynamics, and before starting making calculations, we need to know some units: mass, length, and time. And their units are kilogram, meter, and second respectively. So the correspondence to the standard system units are the mass pound, feet, and second. Remember that we have two systems in the world: the international system and the standard system. And I am calling standard system because that's what it is used in some factories. And you must also know the international system units. So we must manage the both of the systems. And here we have the conversions for that. I will not enter in details, so you can just see them here. And the force is calculated from the second Newton law, and that is why the unit for force is called Newton at the international system. And at the standard system, the unit is the force pound. Okay, another unit that we need to see is the unit of weight, and it is often used gram to express the mass, but the difference between mass and weight is the force, the gravitational force, and it is also determined by the second Newton law. And the weight equals to the mass that multiplies the gravity. And here we have those numbers. I can read them for you, where m is the mass and g is the local gravitational acceleration. That equals to 9.8 meters per square seconds. Okay, and here we have the conversion for that in feet per square seconds, and we also have the unit for work. And work, this is important, is a form of energy. And yeah, work in traditional ways also, like when you're working to your work, like yeah, I am doing some job, well, you are wasting energy or you are consuming energy. So work is a form of energy, and is defined by the force multiplied by the distance. So the unit is the Newton multiplied by the meters, called joule. So the unit for work is joule, and it is a form of energy. And the watt is the time a joule is consumed per second. So when we are making work, we're taking time, and that time that is consumed, it's called watt, and the work done per time is called power. So we're using power to make work. Sorry, we're using power to use work, and we're wasting, or we're consuming watts. So one of the units for power is horsepower, and it equals to 746 watts. Just a little bit of knowledge that you should know, and see that everything is getting related to the topic. And we also have temperature. It is difficult to express temperature in words that define it well, but for example, saying that something is cold or warm will not define the temperature. So I can say that a chair is cold or warm depending on the material it is made, but the truth is that they are at the same temperature. For example, to measure temperature we need the thermometer, and we have properties that change with temperature, and they are predictable and they are repetitive, so we can use them to measure temperature, and we'll call those thermometers. So luckily for us, the thermometer uses a material called mercury, and the mercury acts repetitively and predictable in some sort. So we can take a scale, and start measuring it. So here's a question for you. Well, we have two questions for you. Both of them are very interesting. And what do you think? We're close to a tour bodies when the ambience is cold, and you can post the video. What happens when two persons hug each other? Their temperature raises or decreases. So again, you can post the video, think about the answer, and then boom, here's the answer. The answer is very simple. They share temperatures until they reach equilibrium. We already saw that. And the clothes are not warm clothes, they are just preventing this temperature transfer to the environment. So here we have some photos of animals to see the difference between temperatures. Like in this case, the snake is all blue, it is cold, and the mice is like orange and red or yellowish color, so it is warm. So this is like a very good example of reptiles being cold-blooded. Now you know what you know why, sorry. And here's an example of a thermal equilibrium where iron and copper share temperatures and they reach the same temperature at the end. So what is the zeroth law of thermodynamics? So I will zoom this one, and it says that if two objects are in thermal equilibrium with a third one, they are all in equilibrium. It is very simple. These are fancy words, to be honest. Let's go back to this exercise. So imagine that we're hugging another person, and who says that we're in thermal equilibrium? The one that says that is the thermometer. That is the third one established here. So we have two objects that are sharing temperatures, and then we introduce the third one that will be the measurement instrument, the thermometer. So that's the zeroth law of thermodynamics. I hope it is like a good explanation for that. And we have also temperature scales and units used to measure temperature, like Kelvin, Fahrenheit, and Celsius. And what is interesting about this one is they are based in the freezing point of water and the boiling point of water. And here we have some formulas to do the changes in temperatures to do the conversion, and we also have another one, Rankine temperature. So just check them out, and I think these images are a good explanation point of temperature scales. So another interesting topic is pressure. Pressure is defined as the nominal force that a fluid exerts through an area unit, and this is very important. This is the definition of pressure. But pressure is only defined for liquids and gases, not for solids. Solids have a special kind of pressure that we will call nominal stress. And as the pressure is known as the force per area unit, its unit is the Newton per square meter, also known as Pascal. But Pascals are too small to be measured or to have pressures like this small, so we use kilopascals or megapascals instead. So other common units are the bars, the standard atmospheres, and the force kilogram per square centimeter. Here we have the conversions, and here we have the conversion for the standard system. So a good way to identify pressure and nominal stress is this example. So when we're standing, we are exerting some pressure to the floor and to our feet. The bigger we are, the bigger the pressure our feet will suffer. That's why if we increase the area, the pressure will be lower. So that's why using these snow rockets will give us some movement into the snow, and we will not sink into it because the pressure is expanding through all the area instead of just going into 1 feet. This is just a simple example to differentiate pressure from nominal stress and fluids over solids. Here we have the example with some person that weighs this thing, and we get the pressure unit. Remember that the pressure units are these ones. So one unit that you must be present is the pound per square inch, or PSI. These are very used in industries. So here we are measuring that in PSIs. Okay, and we have another concept that is introduced in pneumatics, but I will state it here because it is important. It is the Pascal Law, and it says that a fluid pressure remains constant in a horizontal direction, and that the pressure that a fluid exerts to another fluid within a recipient is transmitted to all points. So this is the hydraulic press example where you lift a car with the Pascal Law. If we increase the diameter, and then to the other side of the piston, we decrease it, we'll get a lot of pressure transmitting to the other side. But that's another topic for pneumatics. So pressure measurement. So how are we going to measure pressure? So the real pressure is determined by a position called absolute pressure, and it's measured by absolute vacuum. Vacuum, it's the negative pressure. We don't have pressure. So in other words, zero pressure. However, to measure pressure, the devices are calibrated at atmospheres, so they show differences between absolute pressure and local atmospheres. The difference is called manometric pressure. And pressure down the atmospheric pressure are known as vacuum pressure, and they are negative, and they use different devices. So to measure pressure, we use a device called manometer. To measure atmospheric pressure, we use a device called barometer, and to measure vacuum, we use a device called vacuum gauge. So here we have the manometer, the vacuum gauge, and the barometer. So see that this is measured in psi's, this one is measured in mercury millimeters, that's the unit for vacuum, and the atmospheres. Remember that the atmospheric pressure is just the weight of the air that is in a place per superficial area unit, so it changes depending on the height and the weather. That's why we have raining here, cloudy here, sunny here. It will change the pressure of the atmosphere. And here we have some examples from the book that you can use. I will state the book that I'm using at the end, and you can make this. These are very interesting topics that you can use to challenge your brain. It is just like using logic to solve these ones. You have all the information here at the video or at the slides. And this is the book that I am using from Single Genius Thermodynamics. And that's all. I hope you have liked it. This was the first unit for thermodynamics, just very basic concepts, and hopefully we'll see in the next video for unit 2. Thanks. Bye bye.